Hi everybody and welcome. In today's video we're going to be talking about circular motion. So the goal of today's video is going to be looking at some formulas that help us determine basically speed. So we're going to be looking at linear speed and angular speed. So linear speed, if you're thinking about it and you're running on a track on a corner, for example, that would be the actual rate that you are physically moving. So you are running at however many miles per hour. Angular speed is a little bit different. This would be viewing how quickly your angle is changing. So if you're starting off at like the center of the field and the angle reaches out to you, it's talking about, or this is the corner of the track, and right here, it's talking about how quickly is the angle itself. So this measure right here, how quickly is that measure changing as you continue to go around the corner. So it's not actually looking at speed, it's looking at, in radians, basically how fast that moves. So kind of a neat application today, real world, really grounded, very much so in the real world. So some concrete examples that we're going to be doing today, applying it to some real life things. So circular motion, again, here is our linear speed, and then our angular speed is how much that angle is changing. So the formula for this, we have V equals R times theta divided by t divided by time, and theta is in radians. And then for angular speed, we have our W equals theta over t, and again, theta is in radians. So in our first question, we get to practice identifying each of these things and putting them together. So a bicycle tire with a radius of 14 rotates at a rate of 125 revolutions per minute. So the first thing that we have to talk about is identifying theta. So we don't actually see an angle measure given to us here. So the way that we find this is we take the total revolutions per minute and we multiply it by 2 pi. So how many times you go around multiplied by 2 pi. The reason for this, the circumference of a circle is going to be 2 pi, and we're going to times radius. So in this case, our central angle is going to have 2 pi radians as the answer here. So finding theta, that'll be the same thing every single time we do this. Take whatever the revolutions are, multiply it by 2 pi. So 250 pi is our measure for theta in this case. Lucky for us, they define radians explicitly for us. So 14 inches are the radians that we have here. So based off of this, the one final thing that we need is time. So looking at this here, we can look up what unit of time do they give us. Revolutions per minute. So revolutions per every 1 minute. And that's the segment of time that we're given. So we can use our formula from above to plug in. V equals R times theta and divide it by time, which is 1 minute. So it's 14 inches and then 1 minute on the bottom. So when we multiply those together, 14 times 250 times pi, and then divide it by 1, we end up with 10,0995.6, and our units are inches per minute. So that is our linear speed formula. The next one for angular speed, how quickly in radians our angle is moving. It's just pi over t. So we already have, it's just theta over t, sorry. We've already solved for theta, which is 250 pi. Radians is the unit, of course. And then in the bottom, we have 1 minute as our unit of time. So from there, we just simply punch in 250 times pi divided by 1, and we get 785.4 radians per minute. So this idea does work for each of the questions as we go through. So for the second one, we're going to see a very similar situation with our CD. So we have 120 millimeters as our diameter, so be careful there. If diameter is 120, half of that is the radius, so a radius of 60. It rotates at a rate of 45 revolutions, and the unit is minutes. So the first one's asking for linear speed in millimeters per minute, so I like to start off with the radian theta measure. So 45 revolutions times 2 pi, that's going to give us 90 pi radians as our measure for theta. Time, again, per minute, per every 1 minute. And then our radius, like we said, they gave us diameter, which is double radius, so half of that is 60 millimeters. So we can plug in V equals R times theta divided by T. And on top, our unit is millimeters. So 60 times 90 times pi divided by 1 gets us 16964.6 millimeters per minute is the unit. So again, just a little bit of practice plugging in, and as long as we're able to multiply those revolutions by 2 pi, we should be in good shape there. Last piece, again, plugging into our second formula. We have 90 pi as our theta value, and then T of 1 minute. 90 times pi divided by 1 gets us an answer of 282.7. Unit on top is radians, unit on the bottom is minutes. So those are the straightforward examples that we'll see where it's more or less just plug in, use the formula, and we're good to go from there. Example number 5 gives us some practice with changing units. And this is where it gets a little bit tricky today. The same process applies, but we have to remember some old skills to help us out here. So first things first, 16-inch diameter gives us a radius of 8 inches, 500 revolutions per minute. So theta is going to be 500 times 2 pi, radians as the unit, or in this case, 1,000 pi radians. And it's revolutions per minute, so time is per every 1 minute. So as we plug this in, we're going to have radius of 8 inches times 1,000 pi radians, all taking place over a 1 minute interval. Now, what this is asking for is miles per hour, so we have to convert our inches to miles first. So 12 inches are in 1 foot, and 5,280 feet are in 1 mile. And this is called dimensional analysis, where we take conversion factors. If you have inches on the top and inches on the bottom, they simplify. If you have feet on the top and feet on the bottom, they simplify. And you are left with miles, which I realize I just wrote that as minutes instead of miles. So that should be miles right there. So 1 mile and 5,280 feet. If you ever need a conversion factor, just let us know. You can also Google it too, in terms of like how many feet are in a mile, for example. The last thing that we have to do is we have minutes and we want per hour. So we'll change 60 minutes for every 1 hour. And if you're like, Reardon, why are you putting 60 on the top and not on the bottom? Because in order to cancel out, we need to have 1 on the top and 1 on the bottom. So we've canceled all of our units. The only ones that are left are miles and hours. So we know that we've done it correctly. We have miles left on top and hours on the bottom. So from here, we can multiply straight across 8 times 1,000 times 1 times 1 times 60. And then all divided by 1 times 12 times 5,280 times 1 again. And it leaves us with 23.8 miles for every hour. So all of these conversion factors go together, and in this case we don't need angular speed, they just ask for linear speed. So the linear speed that we're going to see in this case is 23.8 miles per hour. So a little bit of dimensional analysis makes it challenging there, but the best way to get confident with these questions is just to practice them, so to get used to converting between units, which the questions on this sheet will help you do. So the following 2 questions, we'll leave those to you. Just like before, I would strongly suggest go through, treat them as practice questions, number 6 and number 7. And if you have questions about how to go through and do them, you'll find uploaded in the teacher notes part of Canvas, you'll see that it is spelled out how each of these questions is solved. So take a look there, you can check your work there. The answers are posted in Canvas. Next, using angular speed to find linear speed. So our formula for linear speed, we have r times theta over time. And what we can see is it's really r times theta over time. And if we view theta over time, if you remember back at our formula here, theta over time, that's just equal to our angular speed. So we can view r times our angular speed. So in this case, just showing us overall that r times w our angular speed, radius times angular speed, does actually give us our linear speed, which helps us solve these things sometimes a little bit more quickly. So angular speed and linear speed, they're related, but not only are they related, they help us with solving some of these things. So reading through our next question, continuing to find some linear speed here. So a ceiling fan, it has 25-inch blades. So if you look at blades on a fan, what you're going to see is those 25-inch blades. Those actually are going to be the radius in this case, because a fan blade does not go completely across a fan, just half of that distance. 40 rotations per minute, so theta is going to be that 40 times 2 pi, or a theta value of 80 pi. And RPM, rotations per minute, so our time is for every 1 minute. We see that there. So from here, we can plug in. So R times theta over time. And they would like this in feet per second. So starting off with inches, 12 inches in 1 foot. Always good to double check here that inches do cancel, leaving us with feet. And then for the next part, minutes. So 60, actually yeah, backwards. 1 minute, because we're going to seconds in every 60 seconds. So minutes cancel, leaves us with feet per second. So on top, we can multiply 25 times 80 times pi. And on the bottom, we can divide that by 1 times 12 times 60. So it should leave us with 8.7 feet per second. So again, more opportunities to practice here. The big idea behind this is identifying radius, finding your theta value, and then finishing up with time and making sure that everything is converted to the correct unit. So if we have these formulas down for today, I'd say the biggest challenge in this skill is converting between unit factors. So good opportunity here to practice that as a skill. As always, let us know if you have any questions, and a strong suggestion would be to fill in any of the examples that we didn't do, and you can go ahead and check your work in Canvas.